Hey everyone, and welcome to this explainer. I am absolutely thrilled to have you here today because we are going to dive into a truly monumental game changer in science. We're talking about how Ernest Rutherford became the very first person to map out and explain the hidden structure of the atom. Before him, the atom was basically just a black box. But through this one incredibly elegant, famous experiment, Rutherford proved that atoms actually have a nucleus, that protons live inside that nucleus, and that electrons revolve around it. So let's jump right in and look at exactly how he pulled this off.
Right off the bat, we're faced with just a massive problem. How on earth do you map a world you literally cannot see? It helps to think of Rutherford not just as a physicist, but as a master detective trying to solve this ultimate microscopic mystery. His goal was really twofold: find out exactly how charges are distributed within an atom and figure out its actual physical structure. But, well, you can't exactly put an atom under a regular magnifying glass. You have to interact with it. You gotta poke it. So Rutherford had to put together a highly specific set of tools to interrogate the atom.
That brings us to Section 1, Building the Detective's Toolkit.
To even get this experiment off the ground, Rutherford needed 3 highly specific, carefully chosen components. First up, polonium. To understand what's going on inside an atom, he knew he had to shoot a charged particle directly at it. It's kind of like throwing a rock in a pitch-black cave just to hear where the walls are. He chose the element polonium because it is an absolute powerhouse at producing alpha particles. And, crucially, alpha particles carry a positive charge. By firing a heavy, positively charged particle into an atom, he could watch how it behaved to figure out what was hiding inside.
But here's the catch. If you just have a chunk of polonium sitting there, it's going to shoot alpha particles everywhere in totally random directions. That is absolutely useless for a precise experiment. So, for his second tool, he enclosed the polonium inside a thick block of lead. Why lead? Because lead easily absorbs those scattered chaotic particles. By drilling just a tiny hole in the block, the lead ate up everything going the wrong way and only let a concentrated, perfectly straight beam of alpha particles shoot out. It essentially became a focusing lens for his microscopic bullets.
Okay, but once you shoot your alpha particles at a target, how do you even know where they go? Alpha particles are completely invisible to the human eye. Enter tool number 3, the zinc sulfide screen. Rutherford completely wrapped his target area with this screen because zinc sulfide has this unique, almost magical quality. Whenever a charged alpha particle hits it, it produces a tiny visible flash of light, a literal spark. This allowed Rutherford to carefully track and map exactly where every single particle ended up after the collision.
Moving on to Section 2, and really the absolute brilliant core of this whole thing, the logic of gold foil.
This brings us to the centerpiece of his genius, the target material itself. Out of all the elements in the universe, out of all the metals we have on Earth, why in the world did Rutherford choose gold foil? I mean, it definitely wasn't just because it was shiny or expensive. He chose it for one strict, undeniable physical property. And that property is malleability. Gold is the most malleable element known to science. This means you can hammer it and press it and flatten it into unbelievably thin sheets without it shattering or falling apart. It just stretches beautifully. And this was the exact, literal, game-changing property Rutherford desperately needed for his experiment to actually work. Just look at this mind-bending number for a second. Because gold is so malleable, Rutherford managed to press his foil target down to a thickness of around 0.00004 centimeters. That is unimaginably thin. We're talking just a few atoms thick here. But why go through all that insane trouble? Why not just grab a normal sheet of metal off the shelf? It all comes down to preventing absorption. If the target sheet was even a little bit thicker, the alpha particles he was shooting at it would just get trapped by the layers of atoms. They'd get stuck, kind of like throwing a tennis ball into a deep snowbank. If he had used tin or copper, the sheet would have just shattered before getting thin enough and the particles would have been fully absorbed. But at 0.00004 centimeters, the foil was so remarkably thin that it basically guaranteed the alpha particles would interact with the atoms and then keep right on going, allowing them to finally hit that detector screen. This incredibly thin sheet was the key to getting perfectly accurate, unhindered results. It is just an absolute masterclass in experimental design.
All right, let's look at what happened. Section 3, 3 astonishing observations.
With this impossibly thin gold foil locked in place, Rutherford initiated the Great Collision. He fired a massive barrage of 20,000 alpha particles straight at the target. And when he studied the flashes on his detector screen, he made 3 distinct observations. First, almost all of the particles, like 19,999 out of 20,000, passed straight through the gold foil as if it wasn't even there. Second, a tiny handful were deflected at small angles.
But third, out of 20,000 particles fired, roughly one single particle completely defied all known physics. It didn't go through, it bounced straight back. Rutherford himself literally said it was like firing a 15-inch naval shell at a piece of tissue paper and having it bounce back and hit you. Just totally wild.
And this perfectly illustrates how a great scientific mind links bizarre observations to monumental conclusions. Let's walk through this logic together. Because the vast majority of particles just zoomed straight through the foil, Rutherford concluded that an atom has to be mostly empty space. Easy enough. But because a few deflected at those small angles, he knew there had to be a positive charge somewhere inside the atom, because his positive alpha particles were being repelled, like repels leg. And because that 1 in 20,000 particle reflected perfectly straight back, well, he concluded that all of that positive charge and almost all of the atom's mass must be crammed into a microscopic, incredibly dense central point, the nucleus.
Which leads us to Section 4, the new atomic blueprint.
Armed with these undeniable conclusions, Rutherford basically tore up the old science textbooks and presented his own completely new model. He proved that an atom has a tiny, ultra-dense central nucleus, which we now know holds the protons and neutrons. He figured out that the electrons are revolving at high speeds around this nucleus, acting a whole lot like planets orbiting the sun. Now, despite this dense center, the overall size of the nucleus is just tiny compared to the whole atom, proving the atom is in fact mostly empty space. Plus, the atom as a whole remains perfectly neutral because the number of positive protons perfectly balances the negative electrons. And finally, that tiny nucleus, it's responsible for holding almost all of the mass and energy of the entire atom.
Now for one last fascinating detail. Section 5, the bullet and the paper.
We really have to address one final brilliant question. Why didn't the negatively charged orbiting electrons attract the incoming positive alpha particles and just stop them in their tracks? Well, think of it using this analogy. Imagine the incoming alpha particle as a super fast-moving bullet. Now imagine the orbiting electron as just a standard thin sheet of paper. Does a flimsy piece of paper have the physical ability to stop a speeding bullet? Absolutely not. The mass and momentum of the alpha particle are so huge, and the mass of the electron is so incredibly tiny, that the electrons simply did not have the physical strength to stop or pull in those fast-moving alpha particles. They just ripped right past them.
Rutherford's experiment wasn't just a massive win for chemistry. It fundamentally changed how we view reality itself. Because if the atoms that make up that gold foil, and the screen, and the air around us, and your chair, and your own body, are mostly empty space, I want to leave you with this one provocative thought. Look around you right now. Tap the table in front of you. How much of the solid world you're touching right now, how much of the reality you experience every single day is actually just entirely empty space? It is a deeply fascinating invisible reality, all unlocked by one brilliant mind and a remarkably thin sheet of gold. Thank you so much for joining me on this explainer, and keep questioning the world around you.